This is a recast of the 7,400-word piece, Advanced Neural Network Techniques, from Schneepat.com. This podcast episode discusses advanced techniques in neural networks, including recurrent neural networks, deep learning, transfer learning, and generative adversarial networks, GANs. It emphasizes the importance of these techniques in various fields such as healthcare, computer vision, and natural language processing. The hosts and guests explain how these techniques work and provide examples of their applications. They also discuss optimization algorithms such as ADAM and SGD for enhancing the performance of neural networks. Let's listen in.
Today, we're diving into the world of machine learning and neural networks. These cutting-edge techniques have been transforming various industries from computer vision to natural language processing. The article explains that understanding and mastering these advanced neural network techniques is crucial for researchers, engineers, and practitioners in the field of machine learning.
That's right. Before we get into the advanced techniques, let's start with the basics. Machine learning is a subfield of artificial intelligence that focuses on developing algorithms and models that enable computers to learn from data and make predictions or decisions without being explicitly programmed. It involves studying mathematical and statistical models, as well as algorithms that allow computers to improve their performance through experience.
And one subset of machine learning techniques is neural networks. These are inspired by the structure and function of biological neural networks. Neural networks consist of interconnected nodes or artificial neurons that process and transmit information, enabling them to learn complex patterns and relationships in data.
Absolutely. Now let's talk about the importance and impact of machine learning in various fields. One field where it's making a huge difference is healthcare. Machine learning algorithms have the potential to revolutionize diagnosis and treatment by analyzing large datasets and identifying patterns that may go unnoticed by human physicians.
For example, in radiology, machine learning models have been developed to detect and classify abnormalities in medical images with high accuracy. By analyzing vast amounts of chemical and biological data, machine learning techniques are also helping researchers in drug discovery to identify potential candidates for new drugs.
That's right. The use of machine learning in healthcare has the potential to improve patient outcomes, reduce costs, and save lives. Now let's move on to advanced neural network techniques.
One popular class of models in advanced machine learning techniques is recurrent neural networks, RNNs. They are particularly effective in handling sequences of data, such as time series or natural language processing tasks. RNNs have recurrent connections, enabling them to store and process information from previous time steps, capturing temporal dependencies and patterns in the data. They are suitable for tasks like language translation, speech recognition, and sentiment analysis.
And it's important to note that there are also variants of RNNs, such as long short-term memory, LSTM, and gated recurrent units, GRUs, which address the vanishing gradient problem and improve their ability to learn long-range dependencies. These advancements make RNNs even more powerful in handling complex data.
Moving on, let's explore a brief overview of neural networks as a whole. Neural networks aim to mimic the functioning of the human brain, capable of recognizing patterns, making decisions, and learning from data. Comprising interconnected nodes or artificial neurons, neural networks process information received through input layers and pass it through hidden layers to produce the desired output in the output layer.
This hierarchical structure allows the network to learn from the provided data and adjust its internal weights and biases accordingly, refining its ability to classify and predict. Understanding the key components and operations of neural networks is crucial for grasping advanced techniques in machine learning.
Absolutely. Neural networks can vary in complexity depending on their architecture. One common architecture is the feed-forward neural network, where information flows only in one direction, from the input layer to the output layer. This simple architecture consists of multiple layers of interconnected nodes or neurons, each containing weights and biases that determine the strength of their connections.
Another prominent architecture is the recurrent neural network, which allows feedback connections, enabling the network to have memory and deal with sequential data effectively. Additionally, convolutional neural networks have been specifically designed for image recognition tasks, utilizing convolutional layers to extract relevant features.
These architectures highlight the versatility and adaptability of neural networks in solving a wide range of problems. Now let's talk about the different types of neural networks commonly used in machine learning.
One such network is the feed-forward neural network. It consists of multiple layers of interconnected nodes without any feedback connections. This architecture is well suited for tasks such as pattern recognition and classification.
On the other hand, the convolutional neural network, CNN, is designed specifically for analyzing visual imagery. CNNs utilize convolutional and pooling layers to extract spatial hierarchy and perform image recognition tasks with remarkable accuracy.
Lastly, recurrent neural networks, RNNs, are characterized by their cyclic connections, enabling them to process sequential data, such as time series or natural language. These different network architectures offer unique capabilities and applications in the field of machine learning.
And finally, one advanced neural network technique that has gained significant attention in recent years is transfer learning. This involves utilizing pre-trained neural networks that have been trained on a large dataset for a specific task and applying them to a different but related task.
Transfer learning allows for the extraction and transfer of learned features and representations from one domain to another, saving computational resources and reducing the need for large labeled datasets. It has been successfully applied in various domains, such as image classification, natural language processing, and speech recognition.
By leveraging the knowledge learned from one task, transfer learning can enhance the performance and efficiency of neural networks in solving complex problems.
That's right. And methodologies like regularization and dropout can be applied to prevent overfitting and promote robustness in the neural network. Fairness metrics can also be incorporated into the model evaluation process to actively measure and address any biases present in the network's predictions. By employing these techniques, developers can enhance the fairness and impartiality of neural networks.
Now let's talk about the advancements in neural network techniques. Deep learning, for example, has revolutionized the field by enabling the training of neural networks with multiple layers. This allows for the automatic extraction of intricate features from large and unstructured datasets. It has proven to be highly effective in various domains, including image and speech recognition, natural language processing, and even game playing.
And let's not forget reinforcement learning. This technique has shown promising results in training autonomous agents to make intelligent decisions and interact with their environment. It has been used to develop autonomous vehicles, game-playing agents, and even robots. These advanced neural network techniques hold great promise for further advancements in machine learning and artificial intelligence.
Absolutely. But as these techniques continue to advance and become more prevalent, we need to address security and privacy concerns. The massive amount of data required for training deep learning models poses a significant risk to the security and privacy of individuals. Malicious actors can exploit vulnerabilities in the system to access sensitive and personal information.
That's a valid concern. Additionally, the black box nature of many deep learning models hinders transparency and understanding of how decisions are made. This makes it difficult to identify biases or errors that can impact privacy. So, it's crucial to develop robust security measures and privacy frameworks to ensure the responsible application of advanced neural network techniques.
Absolutely. Well, that's all the time we have for today. We hope you found this discussion on ethical considerations and challenges in advanced neural network techniques informative and thought-provoking.
Stay tuned for more exciting topics in the world of artificial intelligence and machine learning. Until next time, take care.
Welcome back to our podcast. In today's episode, we'll be discussing a major concern surrounding advanced neural network techniques, which is the increased risks associated with these methods. One of the risks is adversarial attacks, which involve deliberately manipulating input data to deceive neural networks. This compromises the accuracy and reliability of their outputs. Adversarial attacks can be used to fool image recognition systems or bypass security measures.
That's right. Adversarial attacks pose a significant threat to the effectiveness of neural networks. Another concern related to advanced neural networks is data breaches. These networks require large amounts of training data, which raises concerns about the collection and storage of sensitive information. The vulnerability of these networks to cyber attacks and unauthorized access can compromise personal information and lead to privacy breaches.
Absolutely. Now let's move on to the next section of the article, which discusses privacy-preserving techniques in machine learning. Two prominent techniques mentioned are federated learning and differential privacy. Federated learning enables training of models on decentralized client devices, ensuring data privacy by keeping data locally and only sharing model updates. This technique is especially useful in scenarios where data cannot be collected into a centralized server due to privacy concerns.
Differential privacy, on the other hand, focuses on protecting individual data points by adding noise during data analysis. By perturbing the data, differential privacy prevents sensitive information about a particular individual from being inferred. Both federated learning and differential privacy play crucial roles in maintaining privacy while leveraging the power of machine learning algorithms.
Moving on, the article highlights the incorporation of attention mechanisms into neural networks as a significant advancement in recent years. Attention mechanisms allow the network to focus on the most relevant parts of the input data, enhancing its ability to extract meaningful features and patterns. This has shown remarkable improvements in various machine learning tasks such as natural language processing and computer vision.
That's right. By incorporating attention mechanisms, researchers have achieved state-of-the-art results in tasks such as machine translation, image captioning, and object detection. The success of attention mechanisms in enhancing the performance of neural networks has opened up new avenues for further advancements in the field of machine learning.
In conclusion, the advanced neural network techniques discussed in this article are powerful tools for enhancing machine learning models. Techniques such as convolutional neural networks, recurrent neural networks, and generative adversarial networks have shown significant improvements in various applications, including image and speech recognition, text generation, and anomaly detection.
Additionally, the incorporation of transfer learning and reinforcement learning further enhances the capabilities of these advanced neural networks. It's important to note that these techniques are still under continuous research and development, with new advancements being made regularly. Therefore, researchers and practitioners need to stay updated with the latest advancements in order to effectively leverage these techniques in diverse domains.
To summarize the key points discussed today, we explored the significance of deep neural networks in revolutionizing machine learning by enabling the extraction of intricate patterns from complex datasets. We also delved into different advanced techniques such as convolutional neural networks, recurrent neural networks, and generative adversarial networks, explaining their functions and benefits in various applications.
Absolutely. We also discussed the potential future advancements in advanced neural network techniques, such as the development of more sophisticated architectures like recurrent neural networks or transformers. There is also potential for improvement in unsupervised learning and the integration of advanced methods in transfer learning and domain adaptation.
And finally, we discussed the overall implications and potential impact of advanced neural network techniques in various sectors. These techniques have the potential to improve disease diagnosis in healthcare, aid in drug discovery, enhance fraud detection and risk assessment in finance, and revolutionize transportation through autonomous vehicles.
And that's all we have for today. Stay tuned for our next episode, where we dive deeper into the practical implementations of these advanced neural network techniques.
Hey everyone, and welcome back to our podcast. In our previous episode, we discussed the basics of neural networks and their applications in machine learning. Today, we're going to explore some advanced techniques in neural networks as outlined in this article. One such technique is the implementation of recurrent neural networks, RNNs.
That's right, Ben. RNNs are unique in their ability to process sequential data and capture temporal dependencies. This makes them suitable for dealing with time series data, like sequences of text or speech. What sets RNNs apart is their memory units, which allow the network to remember past information and use it to inform future predictions.
Absolutely, Paul. And one popular variant of RNNs is the long short-term memory, LSTM networks. These networks mitigate the vanishing gradient problem that arises during training in traditional RNNs. With their ability to handle sequential data effectively, RNNs have found applications in natural language processing, speech recognition, and machine translation, among others.
Moving on to another advanced technique, deep learning. Deep learning is a subset of machine learning that employs deep neural networks with numerous layers to process and learn from large datasets. It has revolutionized various fields including computer vision, speech recognition, and natural language processing.
Deep learning is known for its ability to automatically extract and learn hierarchical representations of data. This results in highly accurate predictions and classifications. The key process behind deep learning is called backpropagation, where the network optimizes the connections between layers and adjusts its parameters to minimize errors.
Indeed, Ben. Deep learning has solved complex tasks that were once considered challenging, like image recognition. It has paved the way for advancements in artificial intelligence by enabling the algorithms to learn from and process vast amounts of data.
That's right, Paul. Let's delve deeper into the characteristics of deep learning. It aims to replicate the human brain's ability to learn and make decisions. Deep learning is composed of multiple layers of interconnected artificial neurons, known as artificial neural networks. One defining characteristic is its ability to automatically extract relevant features from raw data, allowing for a high degree of abstraction and complex computations.
Absolutely, Ben. Another characteristic of deep learning is its capability to handle and process massive amounts of data. This makes it particularly suitable for applications in image and speech recognition, natural language processing, and autonomous vehicles.
Now let's discuss deep neural networks, which are a key technique in advanced neural networks. Deep neural networks are a type of artificial neural network with multiple hidden layers. These hidden layers enable the network to learn complex representations of the input data, extracting high-level features and making more accurate predictions.
Traditional neural networks cannot capture hierarchies of features like deep neural networks can. This ability to capture intricate patterns in the data is one of the major advantages of deep neural networks. It has led to their success in various fields such as image recognition, natural language processing, and speech recognition.
Moving on to deep learning architectures, there are two prominent examples mentioned in the article: deep convolutional networks and recurrent neural networks. Deep convolutional networks are highly effective when dealing with image data and have revolutionized image recognition tasks.
Exactly, Ben. These networks employ convolutional layers that capture spatial correlations present in the input data. On the other hand, recurrent neural networks are designed to work with sequential data like text or time series. They have memory mechanisms that enable them to retain information from previous inputs, making them ideal for tasks like speech recognition and language translation.
Lastly, let's talk about the applications of deep learning in various domains. In computer vision, deep learning models have revolutionized tasks such as image classification, object detection, and segmentation. By training neural networks on vast datasets, these models have achieved remarkable accuracy in recognizing and understanding images.
And in the field of natural language processing, deep learning has shown immense potential in tasks like sentiment analysis, machine translation, and question answering. By utilizing recurrent neural networks and attention mechanisms, deep learning models have been able to comprehend and generate human-like language, transforming the way we interact with machines in various language-driven applications.
That's a wrap for today's episode. We hope you found this discussion on advanced techniques in neural networks informative. Stay tuned for our next episode where we dive deeper into the practical implementations of these techniques.
Thanks for tuning in. See you next time.
In today's episode, we're going to discuss an advanced technique in the realm of neural networks called transfer learning. This technique involves leveraging knowledge gained from one task and applying it to another related task, thereby overcoming limitations such as lack of data or training time for the target task. Transfer learning has proven to be particularly effective in computer vision and natural language processing domains, where pre-trained models have been successfully applied to various tasks like image classification, object detection, sentiment analysis, and machine translation.
That's right, Ben. Transfer learning is a concept in machine learning that allows us to utilize knowledge gained from training one model to improve the performance of another model in a different but related task. This is especially useful when there is limited labeled data available for the new task. By leveraging pre-trained models, transfer learning reduces the time and computational resources required for training a new model from scratch. It enables the model to generalize well on the new task by benefiting from the broader knowledge captured during the source training. Overall, transfer learning helps enhance the efficiency and effectiveness of machine learning models.
Absolutely, Paul. Transfer learning assists in leveraging knowledge across different tasks by allowing the transfer of learned features and representations from a source domain to a target domain. This is done using pre-trained models. This approach is particularly useful in situations where labeled data may be limited or costly to obtain. By utilizing the knowledge gained from a source task, transfer learning significantly reduces the amount of training required for the target task, resulting in improved performance and faster convergence. Moreover, transfer learning promotes generalization by extracting and applying relevant information across related tasks, leading to enhanced efficiency and effectiveness in solving real-world problems.
There are different techniques for implementing transfer learning in neural networks. One commonly used technique is fine-tuning. Fine-tuning involves taking a pre-trained model, primarily trained on a large dataset, and adjusting the weights on the last few layers for a specific task. This approach saves computation time and leverages the knowledge learned by the pre-trained model. Another technique is called feature extraction, where the pre-trained model is used as a fixed feature extractor, and only the last layers are trained for the specific task. This method is particularly useful when the target dataset is small and insufficient for training a whole neural network from scratch. Both techniques can significantly improve the performance of deep learning models.
Great explanation, Paul. Now let's talk about some successful applications of transfer learning. One example is image classification. Convolutional neural networks, CNNs, trained on large datasets like ImageNet can serve as a base model for various related image classification tasks. By fine-tuning the pre-trained CNN on a smaller dataset specific to the task at hand, researchers have achieved impressive results with reduced computational burden and data requirements.
That's right, Ben. Another successful application of transfer learning is sentiment analysis, which involves analyzing text to determine the sentiment or emotion behind it. Pre-trained language models, such as BERT, have been leveraged in this domain. By fine-tuning these models on domain-specific text datasets, researchers have achieved state-of-the-art performance in sentiment classification tasks, demonstrating the effectiveness of transfer learning in natural language processing.
Absolutely, Paul. Transfer learning has significantly contributed to accelerating advancements in machine learning and has become a crucial component of many real-world applications. With its ability to leverage knowledge across different tasks and domains, transfer learning allows for faster and more efficient training of new models and leads to better generalization performance. This opens up exciting opportunities for developing more accurate and efficient machine learning models, paving the way for potential breakthroughs in various fields such as healthcare, finance, and autonomous systems.
That's right, Ben. One specific technique that has gained a lot of attention in the field of machine learning is generative adversarial networks, or GANs. These networks have revolutionized the generation of synthetic data by using two competing models, the generator and the discriminator.
The generator's job is to create artificial samples that resemble the training dataset, while the discriminator's job is to distinguish between real and fake samples. Through this adversarial framework, GANs are able to learn and generate highly realistic data samples, such as images, music, and text.
GANs have found various applications, including image synthesis, style transfer, and anomaly detection. They are a powerful tool for generating new and unique content autonomously. For example, in image synthesis, GANs have demonstrated exceptional performance in generating realistic images, contributing to advancements in computer vision and graphics.
Text generation is another application where GANs have shown great potential. By training the generator with a given dataset, GANs can effectively generate coherent and contextually meaningful text. This enables applications such as automated storytelling or dialogue systems.
Another important application of GANs is data augmentation. Data augmentation is a technique for enhancing the training dataset by generating synthetic examples. By leveraging GANs, researchers can effectively increase the size and diversity of the training data, leading to improved model performance.
Absolutely, Paul. The training process of GANs involves feeding the generator network with random noise vectors to generate synthetic data. This synthetic data is then compared to real data by the discriminator network. The goal is for the generator to produce data that is indistinguishable from real data to deceive the discriminator.
Through an iterative process, both networks improve their performance by adapting their weights and biases. The generator network plays a pivotal role in capturing the underlying distribution of the dataset, while the discriminator network discerns between real and synthetic data, driving the overall training process towards convergence.
The basic architecture of a GAN consists of these two main components, the generator and the discriminator. The generator takes random noise as input and transforms it into a meaningful output. The discriminator, on the other hand, receives both real and synthetic examples and learns to classify them correctly.
This iterative process induces a competition between the generator and discriminator, leading to the continual improvement of both components. This architecture has proven to be highly effective in producing realistic and diverse synthetic data.
Absolutely, Paul. GANs have opened up exciting opportunities for generating synthetic data that is nearly indistinguishable from real data. With their ability to learn and generate highly realistic samples, GANs have become a valuable tool in the field of machine learning.
And that's it for today. Thanks for tuning in and learning about generative adversarial networks, GANs. Stay curious and keep exploring the fascinating world of machine learning. See you next time.
Hold on, Paul. We still have a lot to cover from the article. Let's dive into the main points, starting with advanced optimization algorithms in neural networks.
Right, advanced optimization algorithms play a crucial role in enhancing the performance of neural networks. One such algorithm is the adaptive moment estimation, ADAM, which combines the benefits of adaptive gradient algorithm, ADAGRAD, and root mean square propagation, RMSPROP.
That's correct. ADAM leverages historical gradient information and adapts the learning rate individually for each parameter in the network. This dynamic adjustment allows the algorithm to converge faster and avoid getting stuck in suboptimal solutions.
Absolutely. Another powerful optimization technique mentioned in the article is the Nesterov accelerated gradient, NAG, algorithm. It improves upon the traditional momentum method by considering the gradient information from the previous step.
NAG achieves faster convergence rates by using momentum to gather information on the instantaneous future direction of the parameters. These advanced optimization algorithms provide effective means to enhance training performance and result in robust and accurate neural network models.
Moving on to stochastic gradient descent, SGD. It's a popular optimization algorithm commonly used to train deep neural networks. Unlike the traditional gradient descent, GD, method that computes the gradient of the loss function with respect to the entire dataset, SGD randomly selects a subset of the training data, known as a mini-batch, to estimate the gradient.
That's right. This randomness introduces noise into the estimation but also provides stochasticity that can help the algorithm escape local minima. Moreover, the mini-batch approach allows for parallelization and speeds up the training process. SGD is widely utilized due to its simplicity, scalability, and efficiency in training large-scale neural networks with vast amounts of data.
However, SGD does face challenges due to its inherent stochastically. For example, it may encounter a noisy loss function that can cause convergence issues. Additionally, careful parameterization is required, such as choosing an appropriate learning rate and balancing the mini-batch size to strike a balance between stability and speed.
Absolutely, Paul, but there are techniques to improve the performance of SGD in training neural networks. One commonly used approach is the implementation of learning rate schedules. This involves adjusting the learning rate during the training process, such as reducing it as the training progresses to allow for more fine-tuning of the model.
Another technique is the incorporation of momentum, which allows for the accumulation of past gradients to guide the current update step. Adaptive learning rate methods such as ADAGRAD, RMSPROP, and ADAM dynamically adjust the learning rate based on the parameter's history to achieve faster convergence and better overall performance.
These techniques enhance the efficiency and effectiveness of the SGD optimization process. And speaking of recent advancements in SGD variants, ADAGRAD and ADAM have significantly contributed to the optimization process.
ADAGRAD is a gradient-based algorithm that adapts the learning rate for each parameter individually, enabling faster convergence in scenarios with sparse data. On the other hand, ADAM combines the best features of adaptive learning rates and momentum methods, resulting in improved optimization performance.
These recent advancements in SGD variants have revolutionized the field, providing enhanced optimization capabilities and enabling the training of more complex neural network models with improved efficiency and accuracy.
Absolutely, Ben. And let's not forget about recurrent neural networks, RNNs. They are particularly effective for sequential data processing tasks, as they have the ability to remember past information and use it to make predictions.
That's right. However, RNNs suffer from the vanishing gradients problem, which hampers their ability to learn long-term dependencies. To address this issue, variants of RNNs such as long short-term memory, LSTM, networks and gated recurrent units, GRUs, have been developed. These variants have gating mechanisms that enable them to selectively retain important information over longer sequences, making them more effective in handling sequential data.
That's a great summary, Ben. It's fascinating to see how these advanced optimization algorithms and techniques are improving the training performance and overall capabilities of neural networks.
Absolutely, Paul. It's an exciting time in the field of machine learning, and we can't wait to see what advancements will come next. One of the major challenges in training large-scale neural networks is the computational complexity involved. As the size of the network increases, so does the number of parameters to be learned. This requires more training data and computational resources. Additionally, training such networks can take weeks or even months to complete.
That's right, Ben. And with the increase in size, there's also a higher risk of overfitting, where the model memorizes the training data instead of learning meaningful patterns. To mitigate this, regularization techniques like dropout and weight decay are employed.
Another challenge is finding a robust optimization algorithm tailored for large-scale models. Traditional optimization algorithms become less effective as the complexity and size of neural network architectures increase. They have drawbacks like slow convergence and difficulty in choosing appropriate learning rates.
To address these challenges, various advanced optimization algorithms have been proposed. One example is stochastic gradient descent, SGD, and its variants. These algorithms use random sampling techniques to estimate the gradient of the objective function, allowing for efficient optimization of large-scale neural networks.
However, SGD suffers from issues like slow convergence and difficulty in choosing appropriate learning rates. To overcome these challenges, advanced optimization algorithms like ADAM, RMSPROP, and ADAGRAD have been developed. These algorithms leverage adaptive learning rates, mode estimation, and gradient attenuation techniques to significantly improve the training efficiency and stability of large-scale neural networks.
That's right, Ben. These advanced optimization algorithms have revolutionized the field of machine learning by improving training times and stability. They allow for efficient optimization of large-scale neural networks by adapting the learning rate for each parameter based on their prior history.
Moving on to the next point, parallelization techniques and distributed training have emerged as powerful approaches to accelerate model training. Parallelization involves breaking down the training process into smaller tasks that can be executed simultaneously on separate processing units.
By exploiting the computational power of multi-core processors or distributed computing systems, parallelization greatly speeds up the training process. On the other hand, distributed training allows multiple machines to collaboratively train a model. Each machine processes a subset of the data and shares its results with others, establishing a collective learning dynamic.
These techniques have revolutionized the field of machine learning by significantly reducing training times and enabling the processing of massive datasets. They have made it possible to train large-scale neural networks on extensive datasets in a reasonable amount of time.
Now let's talk about some specific optimization algorithms for large-scale neural networks. Two popular algorithms are mini-batch gradient descent and Adam-Wu mini-batch gradient descent divides the training data into small batches and computes the gradient of the loss function with respect to the parameters using these mini-batches.
It then updates the parameters based on the average gradients computed over the mini-batches. This allows for more efficient optimization of large-scale neural networks by using smaller subsets of data for gradient computation.
Adam-Wu, on the other hand, is an adaptive optimization algorithm that combines both momentum and RMSPROP techniques. It adapts the learning rate for each parameter based on their prior history and can effectively handle sparse gradients.
These optimization algorithms are crucial in achieving satisfactory results when training large-scale neural networks. They improve convergence speed, stability, and overall performance of the models.
Absolutely, Ben. And these advancements in optimization algorithms have had a significant impact on real-world applications as well. For example, in image recognition, neural networks are trained on extensive datasets to accurately identify objects or patterns within images.
This has been pivotal in fields like self-driving cars, surveillance systems, and medical diagnostics. By processing vast amounts of data and learning complex patterns, neural networks have greatly improved the accuracy and efficiency of image recognition systems.
Language translation has also greatly benefited from large-scale network training. By training neural networks on vast amounts of text data, these systems can accurately translate between multiple languages, aiding in international communication and breaking down language barriers.
These examples highlight how the ability to process vast amounts of data and learn complex patterns has revolutionized these applications and greatly improved their accuracy and efficiency.
However, it's important to note that the increasing complexity and size of neural networks have led to computationally intensive training and inference processes. To address this challenge, advanced neural network techniques have been developed.
One such technique is transfer learning, which leverages pre-trained models to perform task-specific learning. By transferring knowledge from a pre-trained model, the training time and computational resources required for a specific task can be significantly reduced.
Another technique is generative adversarial networks, GANs, which have revolutionized computer vision by enabling the creation of realistic synthetic images. GANs use a generator and discriminator network that compete against each other to produce high-quality generated samples.
These advanced techniques have opened up new possibilities in artificial intelligence research and application development. They have allowed for more efficient training and inference processes, pushing the boundaries of what neural networks can achieve. However, with these advancements come ethical considerations and challenges. One significant concern is the perpetuation of bias and discrimination by neural networks. You see, neural networks are trained on vast amounts of data, but this data often reflects human biases and prejudices. So if the training data is biased or contains discriminatory patterns, the neural network may learn and reinforce these biases, leading to unjust outcomes.
That's right. And this can have serious consequences in various fields, such as healthcare, finance, and criminal justice. For example, if a neural network is trained on biased data in the criminal justice system, it may lead to unfair and discriminatory decisions when determining someone's guilt or innocence. This is why it's crucial to address bias in neural network models.
Absolutely. And researchers are actively working on developing methods to detect and mitigate bias in neural networks. These methods include techniques like debiasing algorithms, fairness-aware training, and bias detection algorithms. The goal is to achieve fairness in neural networks and ensure equitable outcomes for all individuals.
However, achieving fairness in neural networks is a complex and ongoing challenge. It requires a thorough understanding of the underlying biases and a continuous effort towards developing fair and unbiased models. It's not something that can be solved overnight, but by actively working towards it, we can improve the fairness and impartiality of neural networks.
Another ethical challenge associated with advanced neural network techniques is the lack of transparency. You see, complex neural networks are often seen as a black box, meaning it's difficult to understand how they reach their decisions. This lack of transparency raises concerns about accountability and the ability to challenge or explain the results produced by these advanced techniques.
And this is a big problem because transparency is essential when it comes to making important decisions that impact people's lives. If we can't understand how a neural network reached a particular decision, it becomes challenging to ensure that the decision was fair and unbiased. So, developing transparent and interpretable machine learning models is crucial to addressing this ethical challenge.
Absolutely. And there are techniques being developed to address this challenge as well. One such technique is careful data preprocessing, where steps are taken to eliminate any biases in the training data. Additionally, using diverse data sources to train the neural network can ensure that it is exposed to various perspectives and experiences, making it more robust and less biased.